So this video will be the concluding pieces of number 6 from 2010 Form B of the AB exam. And they give us two particles position functions, and in part C here they ask us to find the acceleration of particle P at 3 and then decide if particle P is speeding up, slowing down, or neither at that time, and try to explain why. So I've kind of copy and pasted a little bit of the work that we had done in a previous video in part B. And this is a sign chart that we made for the derivative of P. So the velocity of particle P is negative from 0 to 4, and then it's positive from 4 to 6. And then this was the derivative of P, or the velocity function for P. So I cleaned it up a little bit. This was the initial form of it that we had right here from using the chain rule, and then I just kind of multiplied the -1, the 2, and the pi by 4 together to get negative pi by 2 as the coefficient of the sine function. And what we need to do in part C here is find the acceleration of particle P. So the acceleration of particle P is going to be given by the second derivative of position. So the second derivative of position is going to give acceleration, so we need to take one more derivative here. This right here is a constant, so I'm just going to copy that into my derivative. So copy the constant, and then the derivative of sine of pi by 4 times t is going to require the chain rule, and so we'll do the derivative of the sine function, which is cosine. We'll have to leave the inner function inside this cosine function, and then we'll have to multiply by the derivative of this inner function right here to finish off our chain rule. And the derivative of a number times t is just going to be the number, so it's kind of a goofy looking number, but pi by 4 is just a constant. And so this would be our second derivative. Now what they want us to do with this is they want us to use it to find the acceleration of particle P at time 3. So really what we want to do is we want to try to evaluate P double prime of 3, which is going to correspond to the acceleration of particle P at t equals 3. So I see that this times this is going to give me, when I do top times top, I'm going to get pi squared, and when I do bottom times bottom, I'm going to get 8. So I'm basically just multiplying the constant here with the constant here, and then I'm going to have to take that value and multiply cosine of pi by 4 times 3 by it. And so if we think about how we're going to go about evaluating this, we probably want to simplify the angle that's inside this cosine function a little bit. So I'm just going to copy down the ugly constant that we determined on the previous line, and then inside the cosine function, if I do, top times top, bottom times bottom, I'm looking at 3 pi by 4. And so now it's a matter of figuring out what cosine of 3 pi by 4 is. And if you use the unit circle in order to help you determine this, find the angle 3 pi by 4. So 3 pi by 4 would be, well, let's see, 4 pi by 4 would be clear from this point to this point, because that would correspond to pi. But 3 pi by 4 is going to be, let's see, pi by 4, another pi by 4, another pi by 4 is going to kind of put us smack dab in the middle of the second quadrant there. And so what we want to go ahead and do is determine the cosine of this angle on the unit circle. Right? So we want to know the cosine of this angle, 3 pi by 4. And it's not that nice of a situation because we don't sit at one of these nice locations on the x-axis or the y-axis. So we're going to have to try to figure out what the x-coordinate of this point is, since we want to know the cosine of that angle. So if we want to know the cosine of that angle, I think what we can go ahead and do is we can use our left hand trick, or if you remember your 45-45-90 ratios, you would be able to use them to help you figure out what the x-coordinate of that point is. I'm going to go with the left hand trick, and so if I try to do this with let's see, I guess this would be my thumb, this would be my pinky, and then I'd have ring finger, middle finger, index finger. So our middle finger would correspond to the angle of pi by 4 in the first quadrant. So if we pulled this finger in, we're looking for cosine of the angle, so we would count how many fingers remain above the one we've pulled in. Well, we've got 2 fingers remaining above the one we've pulled in, and so what we would do is we would take that number of fingers, 2, put it under a root, and always put our answer over 2. So the cosine of pi by 4 is going to be equal to this by using the left-hand trick. We wanted the cosine of 3 pi by 4. So if you think about this, this triangle right here would be congruent to this triangle right here. We've basically just determined that this x value is going to be square root of 2 over 2. This x value over here, since these triangles are congruent, the absolute value of this is going to be square root of 2 over 2, but since we're going to the left of the y-axis, cosine of 3 pi by 4, which is really what we wanted here, is going to be negative square root of 2 over 2. So it's kind of an ugly value. We just want to take this value and we want to put it in place of cosine of 3 pi by 4. So the second derivative evaluated at 3 ends up being negative pi squared over 8 times negative square root of 2 over 2. If you want to clean this up a little bit, it does get a little nicer because it's a negative times a negative, so your answer is a positive. And then you're going to have the pi squared still times the square root of 2 in your numerator. And then when you do bottom times bottom, you end up with 16. So this would be the acceleration of particle p at t equals 3. What is happening with the speed of particle p at this time? Is it going up, going down, or doing neither? Well, what you need to do to answer questions about speed is you not only need to look at acceleration, you also need to look at velocity. So at the t value of 3, the velocity of particle p is negative. So if the velocity is negative and we try to sketch a little piece of a velocity graph here, at 3 what we know is we know our velocity graph is going to be below the t-axis. We know that basically from this sign chart, right? So this is a graph of velocity or a graph of p prime. Our velocity has to be negative at 3 based on the sign chart. Our acceleration has to be positive, and acceleration is the derivative of velocity, and so basically what we'd have to have going on at the t value of 3 on our velocity graph is we'd have to have a positively sloped tangent line given this positive acceleration value. And if we have a positively sloped tangent line and we're below the x-axis, our velocity graph is going to be getting closer to 0 on that interval. And since velocity is getting closer to 0, what we know about speed is that our object is slowing down. If our velocity would have been moving close away from 0, our object would have been speeding up. In part D here, it says write but did not evaluate an expression for the average distance between the two particles on the interval from 1 to 3. Now before we try to focus on average, let's focus on distance between the two particles. Well, if I take r of t minus p of t, this isn't going to be the distance between the particles. It will be the distance between the particles when particle r is further to the right than particle p is, or has a greater position than particle p. But if particle p has a bigger position than particle r, then this quantity is going to be negative. Well, we can turn this into a distance between the two by slapping absolute values around them. And then if particle p is actually further to the right of particle r, when this quantity becomes negative, the absolute values turn it into a positive. So this expression would represent the distance between the two particles. Now, if we want the average distance between the two particles, and this function that we just defined here represents the distance between the two, we have this formula from out of chapter 4 of our book that lets us find the average value of a function. If we went ahead and we evaluated this expression, we would have a result that represents the average distance between the two particles on the interval from 1 to 3. Doesn't ask us to evaluate, so here is our distance between the particles function, and then we turned it into an average calculation of that function by using the integral and multiplying by this coefficient.